All right. We are in the home stretch, right? November, in more ways than one, right? Elections tomorrow, all the political ads, all of these texts that I'm getting multiple times a day, ending. Can't wait for that. All right, so we have a lab this week. We're going to do some community similarity. Hopefully you set up your allelopathy stuff. Thursday, it's not too late. So on Thursday's lab, you can still get your set up. Monday, Tuesday, Wednesdays, yours should have been set up so that it is leaching out, that water is leaching out any chemical in that plant material. Make sure you bring it. We'll get those set up this week in lab, and then next week we'll collect our data and test to see if there's any evidence of allelopathic effects. All right. We have our exam is next week, Friday, I believe. Next week, Friday, because then the final exam's the week after that. So there's not a whole lot of time left. Not a whole lot of time left. All right, so we were talking about population growth. We talked about exponential growth and how we had the 5 assumptions related to it. And one of the big assumptions was that we have a constant R, a constant intrinsic rate of growth that doesn't change. Well, that's probably the assumption that's violated, because we know that resources aren't limiting. And so when you have populations that are growing, they reach a certain size, then you start seeing competition for those resources, which then changes either birth rates or death rates or immigration rates. All right? If you change one of those, you're going to change your intrinsic rate of growth. So we introduced the exponential growth equation as the equation that we would use to estimate change in population size and also estimate population size at a certain time point. That made all of those assumptions. We then went ahead and introduced a different equation, which was our logistic growth equation. So our logistic growth equation, let's pull that down. Our logistic growth equation, we weren't using it to estimate our population sizes. We were actually using it to estimate change in our population size. So our dn over dt, that's our change in our population size, is equal to r times n. That's our exponential growth equation. All right, this is part of our exponential. And then what we did was we introduced a density dependence term. And one that I like using is this, 1 minus n over k, where k is our carrying capacity. This term in the parentheses is our density dependent terms. That's going to be modifying our intrinsic rate of growth, r. All right? At least mathematically, that's kind of what it's doing. So I asked you then to get some practice with this equation to answer these questions using this equation. All right? And that is what we are going to go over. So, question 1. Get some more room out here. There we go. All right, so question 1, yeast exhibit R of 0.25. So that's given in our equation, all right? And we know, I said in the equation that the vial can hold 1 million yeast cells. So that's our carrying capacity. All right, so the first question was, what's the population growth rate when we inoculate the vial with 100 cells? And that could be a realistic situation, especially if you're growing yeast or growing bacteria. You know the maximum population size that you can grow in a vial, and then you end up pitching a smaller amount to try to grow up to that size. So our first one is, let's say this is number 1. What if our n is 100? Well, we have everything we need in our equation. So first off, is our population going to be growing, declining, or staying the same? It's growing. Why? R is greater than 0, and we're below our carrying capacity. All right, so we're below our carrying capacity. We're far from it. So yeah, we're going to see population growth. So we're going to see dN over dt is equal to 0.25, that's our R, times 100, times our density dependence term. All right. So what do we have? Oops, where's my calculator? So I know you guys can't see it here, but those at home can see it. So here's our calculator. We have 0.25 times 100 times, parentheses, 1 minus 100 divided by 1 million. $24.9975, yep. What's that? Is it 1,000? It is. It is. Let's fix that. Slight change. Let's fit 2 zeros in here. There we go. Well, we did a 1. Yeah, I guess you guys can see it, right? You guys can see it. There it is. All right, let's try this again. 0.25 times 1,000 times, parentheses, 1 minus 1,000 divided by 1 million. About 250. And my units, I didn't give my units, but maybe this is cells per hour. Units would correspond to whatever units that is. So that's not too bad. So our second question then says, what happens if we have 500 yeast, 500,000? All right, same thing. We just plug it into our equation. We have our R, we have our N, and we know our K. Go back to our calculator here. So let's see here, clear. 0.25 times 500,000 times 1 minus 500,000 divided by 1 million. Whoa. One less 0. Let's try this again. 500,000 times 1 minus 500,000 divided by 1 million. That's better. 62,500. 62,500 cells per hour, perhaps. Cells per 2 hours or 3 hours, who knows? So our last one increases our population size. I'm going to do this over here to 900,000. All right, so at 1,000 cells, we had a growth rate of 250. At 500,000, we had a growth rate of 62,500. What do you think our growth rate is going to be? More than 62,500 or less than that? More than this number or less than that number? What do you think? Less? Why do you say less? Because it's near the carrying capacity. Also, this value is half of our carrying capacity. What's important about that value? K over 2. It's our inflection point, and it's a point of maximum growth. So our maximum growth rate, that's it. 62,500 cells per hour, cells per 2 hours, who knows? So we know we're going to get a value that's below that number. So just plug it in. $900,000 over $1 million. Let's try this out. 0.25 times 900,000 times parentheses 1 minus 900,000 over 1 million. Jeez, oh Pete. Close it. 22.5. $22,500. So is it below? Yep, it is. And that's we should recognize it. It's this was half the carrying capacity. This is going to be our maximum rate of growth, 62,500. Questions? All right, no questions? We will move on. All right, so those are density-dependent factors. All right, those are factors that change R as our population size changes. We also have density-independent factors. These are going to be the factors that change R in some way, but they change them independently of our population size. So I showed you a graph of density dependence where as our N changes, as our N increases, our birth and death rates changed. When we have density independent factors, and what we have is birth rates and death rates and immigration rates and emigration rates, they all stay the same. They don't change at all. All right? So what are some examples of these density independent factors? Weathers, that's a primary one. Disturbances, anything that's unrelated to the population itself. All right? These factors, these events, are unpredictable by nature. And because they're unpredictable, their effect on our population dynamics is to add noise. It's to add uncertainty. It's to add randomness to our population sizes. All right? This is the reason why when we look at population growth and population dynamics, this is why we see populations bouncing around. They don't stay at a fixed number because of all of these density-independent factors. Some of the factors are going to be very strong. You know, wildfires out west. That's a very severe density-independent factor. Others are going to be very minor. You know, not getting rain for a week. You know, when we normally get rain, let's say once every 5 days, that's going to have a very minor effect on the population, but it still has an effect. It can still cause an increase or decrease in our population. All right? Questions? It's about all we're going to say about density independence. Now this leads us to our regulation. All right, so we talked about density-dependent factors and how they influence R. We talk about density-independent factors, the weather events. What ultimately leads us to regulation of a population? Normally regulation, or at least population regulation, includes all of those mechanisms that determine our population size by the density-dependent factors. These are going to be the factors that regulate our population in some way. And it acts in kind of like a negative feedback loop. Whereas our population sizes increase, you're going to see usually increase in mortality or a decrease in reproduction. That leads to a population decrease, which then causes mortality to decrease, reproduction to increase, and then the population increases and so forth. So you can get this cyclical cycle of feedback from our population itself. Now that would give us very nice dynamics, basically give us periodicity and nice fluctuations, regular fluctuations, except for those density independent factors. They're going to be adding the noise to this, which will cause us maybe to increase faster than what we should have, or to decrease faster than what we should have. All right? Now, how does that work? It could change the magnitude of our interactions. It could increase the effect of competition. It could decrease the effect of predation and so forth. Or in some cases, it may actually prevent our population from ever reaching the carrying capacity itself. So, let me show you a graph like that. So we have a population regulatory mechanism at work. All right, it's going to be fully functional, but then when you have these density independent factors adding the noise, it could act kind of like as a reset switch. So let's say we have a graph where we're plotting our population size. We'll say this is our carrying capacity, keep it simple. All right, this is where population will get us to. And what could happen is that our population is doing fine, it's growing, it's growing, it's growing, it's growing, and then all of a sudden a disturbance happens and causes us to drop. And then we start increasing again, and then another disturbance. And you can see that every time we start to grow up, a density independent factor happens that kind of acts as a reset switch and pushes us back down. And in some cases then, those density independent factors are actually keeping us well below our carrying capacity. So population wants to grow, but it's our density independent factors that say, hey, okay, we're going to stop, we're going to let you reset. All right, so density dependent factors, that's acting more like our feedback loops. Density independent factors are acting more like a reset switch. And this type of population control, population dynamic pattern, forms a basis of something called non-equilibrium ecology, where it says we're not actually going to ever get to our carrying capacity because of all of the randomness that's happening, all of these extreme weather events. It seems to model some of our marine invertebrates quite well, and probably some of our terrestrial invertebrates as well. All right, so population regulation, it's all about our density dependent factors, and that density independent factors, those add noise. All right, so summary. No population can grow indefinitely. We introduced the exponential growth equation and assumed that they could, but in reality they can't. We have our regulatory factors that are going to be acting, and they're going to act on birth rates, death rates, immigration rates, and or emigration rates. Maybe it's just one, maybe it's all four of these that it's acting on. Okay? So what are these regulatory mechanisms? Well, our regulatory factors kind of can be grouped into paired mechanisms, and these mechanisms limit growth. So you have your biotic versus abiotic factors. That's kind of our first paired mechanism, or first paired distinction at least. We have top-down factors and bottom-up factors. So those factors that act from top of our food chain down to the bottom, or those bottom-up factors where it's more of like our food source controlling and regulating those higher levels. And then we also introduced this idea of density-dependent versus density-independent factors. We said those density-dependent factors act in like a feedback mechanism, and then the density-independent factors are more about adding noise to our populations. Any questions? Any questions on those remote viewers? Okay. Let me get these released. Make available. Oops. Yep. Yeah, that is. All right. So you're going to be getting a series of emails from Blackboard letting you know that stuff is available. And make available. Yes. Whoops. No. Display until. All right, first up, get this out. Here's our Blackboard. So we had population growth. That was exponential growth, calculating, estimating population size, change in population size, and doubling time. All right. Second one, we have these three that just went live. Let's edit mode off. All right, so practice problems, density dependent practice. These are example problems, just kind of what we did here up on the board. They're going to give you opportunity to practice some of these, work them out yourself, and then I posted a YouTube link that kind of shows you how I answered them. So you can use that to check your answers, see if you did them correctly. When you feel confident, then I have this set of 5 questions. These are ones that you'll answer on your own. Save the answer, save the sheet. You will enter them into this homework number 2 quiz. All right, it's just like the first one where you entered your number. I asked you to round to the whole number. You have 3 attempts, and I think I've set it up correctly, so after each attempt, it'll tell you which one you missed, if you missed it. All right, so the first attempt, Cameron maybe emailed me. Someone emailed me because they weren't getting the right answer. And on the first problem, I don't normally include commas on large numbers. So the answer key didn't have the commas. And if you included a comma, it got marked wrong. That was fixed. So I did the same. For this one, I did include the possibility that you can include a comma or you don't have to include a comma. It shouldn't matter. But this gives you practice. This quiz, have to have it uploaded, your answers uploaded by the end of the day on Friday. All right, so this is giving you practice. Those questions of this type will be on the next exam. And that next exam, you'll need scratch paper, you'll need a calculator so that you can do those problems. Also, since we finished this presentation, the quiz. The quiz will go live. You have until the end of the day on Wednesday to do it. So I'm going to give you more time for the homework because if you go through it and you have questions, you're not getting the answers or you don't know how to do those answers, you can bring your questions to class. You can email me before class and I'll address it at the start of class. Because if you have a question, other people might have the same question. The quiz will be due at the end of the day on Wednesday. You don't need that extra time because the quiz does not have the calculations on it. The quiz is just more the content of the presentation. So definitions, multiple choice, multiple answer. I think there's 1 or 2 true-false questions on it. All right, so the calculations are going to be separate. That's part of that homework quiz. And then our regular lecture quiz is due at the end of the day on Wednesday. Oh, let me go back there. Still logged in. So I didn't realize it. Some of you probably use the Blackboard calendar to see what's due. Is that correct? Some of you do. I guess I have to put a due date on here in order for it to show up. Thanks to a grad student who made me aware of that. All right. One thing's added, and let's get that problem set quiz. Make sure you do, when you upload your answers, make sure you have the answers done. You only have 5 minutes to input your answers. That's not a time for you to open it up and work through the problems at that time. That's why I did the PDF questions, so that you can do it on your own time. And then when you're ready, go ahead and upload the answers. All right. That should be good. All right. Moving forward. All right. So we introduced density dependence, density independence, and hopefully you kind of recognize that they don't really just operate independently of each other. You don't always just have a single regulatory factor, operating to regulate a population. You've got many factors that are going to operate. Now, there may be one factor that dominates at any one time, but all of these factors are acting together to try to regulate a population. So that's what we're going to talk about. And to start talking about this regulation, we're going to make the distinction between population equilibrium and population stability. All right? So I'll start with equilibrium. Equilibrium is a special case of population stability. So both terms tell us that a population is fluctuating within narrow limits. Now, both terms tell us that. They're going to fluctuate within narrow limits. So on this graph, I could say our population may be fluctuating right within those limits, and they would always fluctuate within these limits. All right? That's a case of population stability. If we were up here near our carrying capacity and fluctuating, we are also fluctuating within narrow limits. We are also fluctuating within narrow limits, so this is also population stability. But this is also population equilibrium because we are fluctuating around that carrying capacity. So that's really the distinction. If we're fluctuating around the carrying capacity, we're at equilibrium. If we're not at our carrying capacity, we're not at equilibrium, but we can still be stable. All right? We can still be stable. What causes this fluctuation? It's the summed effects of all of our regulatory factors. It's our density-dependent factors, and it's the density-independent factors. They're all working together to get us to fluctuate within these narrow bands. Now, when we have these bands, we can oftentimes pick a number where we are centered around. And at that number, we normally say that we're fluctuating around an equilibrium population size. And that kind of sets it up separately from a carrying capacity. So our equilibrium population size doesn't necessarily need to be our carrying capacity. Sometimes it is, but oftentimes it's not. And oftentimes it's below that carrying capacity. All right? So an important thing to know is that our density-dependent control doesn't always result in stability. A great example of this is predator-prey interactions. There's a pretty good study that was done, man, I bet 80 years ago now, at least 60 years ago, where they tried to get this nice periodic fluctuations between predator and prey populations. This is a great example of top-down regulation and bottom-up regulation, because the predator regulates its prey, the prey regulates the predator. And he could never really get the population stabilized. In every single case, you'd get it, you'd have the increase in the predator, and then the predator basically wipes out the prey. Prey population crashes to zero, and then the predator population crashes to zero. And it's something similar kind of happens here between snowshoe hares and lynx. So that study, it was actually done in a lab setting. It was done in a lab setting. Here is actually out in real life. So in years, you can see that the populations fluctuate, but most importantly is that the lynx population was unstable. It crashed. All right? You have density control mechanism, density dependent control, the bottom-up effect of the prey, but that wasn't enough to help sustain and support our predator populations. So know that we can be stable, and it's a sum effect of all of our density dependent and density independent factors. But just because we have density dependent factors happening and operating doesn't mean that we can result in stability. One does not lead to the other. Now, in these regulatory mechanisms, we've been kind of focused on more of those external things to the population: competition, predation, parasitism, diseases, and that sort of thing. But we also have some factors that are internal to our population. These are things that you might not have considered. We term these self-regulation. They're internal density-dependent processes that operate independently of what's happening outside of our population. It happens independently of the biotic factors that they're experiencing and the abiotic factors. Now, I'm going to note that if a population self-regulates, R must change as our population size changes. Key point. R must change as our population size changes. The two things that we're going to talk about is territoriality and stress. Both of these are internal regulatory mechanisms, things that regulate our population or can regulate our population. So we're going to start with territoriality. So organisms that are territorial usually exhibit a correlation between their mating success and the possession of territory. So if you have a territory, your mating success increases. If you don't have a territory, your mating success decreases and probably goes down to zero. All right? So how does this regulate our population? Well, as our population size and population density increases, two things happen. One, our birth rate declines. Why? Because you have a larger number of individuals that do not hold a territory. If they don't have a territory, they're not mating. If they're not mating, they're not replacing themselves in our population. So you would then see a decrease in our population size. R changes because B decreases. The second thing, because our population size increases and because you have a lack of territories, you start to see an increase in our emigration rates, increase in E. Why? It's because our individuals, they're trying to find territory, there's none available, so they're going to disperse, try to get to a new area where they can possibly find more economic resources. R changes again because E increased. So territoriality actually works to regulate a population through two processes: by its effect on our per capita birth rate and its effect on our emigration rates. Questions on territoriality? Great study. I think your book talks about it. The study has to do with grouse. Red grouse are territorial. They need a territory. And it's very clear to see that when all individuals have a territory and there's a bunch of them that don't, the birth rates decline. Population size declines shortly thereafter. Stress is the second internal regulatory mechanism. How this works is called the social stress hypothesis. This hypothesis says that the pathological effects of crowding ultimately lead to a decrease in reproduction. How does this work? Well, I've kind of made a flow chart here, and I would have preferred it having vertical or horizontal, but because of our presentations, I wanted to get everything on this one slide. So here's the idea. You increase your density in our population. So population size increases, density increases. That's going to stimulate two different things in individuals. One, it's going to stimulate aggression. Why does it stimulate aggression? What's that? More competition for resources. Our population size increased, the amount of resources available per individual declines, which means if you want to get it, you're going to have to be more aggressive. The second thing is that we have an increase in stress. Why do we see an increase in stress? Weston. Same reason. Increased competition. There's this fight for the limiting resources. So you have an increase in aggression and an increase in stress. Both of these behaviors, stimuli, lead to an enlargement of the adrenal gland. All right? Leads to an enlargement of the adrenal gland. These individuals are trying to get those limiting resources. As these hormones from the adrenal gland increase, they actually inhibit our reproductive hormones. You inhibit reproductive hormones, you have less desire to mate, and even when you do, you're going to probably have less success. So all through this increase in density, you have this physiological change that takes place that decreases reproductive rates. That's our social stress hypothesis. Are these two, territoriality and stress, the only internal regulatory mechanisms? No, there's a couple other ones. Your book might mention a few more, might give an example or two, but I'm not going to present those. Questions? So we've got density-dependent factors, both external to the population and internal to the population, and you have our density-independent factors. All of them can regulate a population, and in fact, all of them work in combination to regulate our population. But which ones are dominant changes through time. And the only reason we know this is through some long-term studies. You don't see this if you go out and study a population for a year, or for 2 years, or maybe even 3 years. You have to study this population over 10, 20, 30, maybe even 40 years to see this type of patterns, these types of effects. So the example here is Isle Royale on Lake Superior. It's an island in the lake. All right. It's located some distance from shore, which makes it hard for land mammals to colonize. All right, they're not really going to be able to swim across the lake. Now, research here, observations here started well below 1910, or well before 1915, where moose first colonized. They were there, moose weren't on this island. And what has been proposed is that we had an unusually harsh winter, cold winter up there, that caused Lake Superior to freeze, or at least form an ice bridge between the mainland and the island itself. All right? That allowed moose to cross the island, or cross that ice bridge to get to the island. Now, maybe the moose did a little bit of swimming, but they made it there. All right? So the moose colonized, and then they started recording the number of moose. And you can see that moose populations, what kind of growth curve does this look like? Exponential, logistic, what do you say? Which one? Yeah, kind of exponential. Maybe you could say maybe it's starting to flatline. I don't know, it's kind of difficult because we only have, points every 5 years. But yeah, I mean, we've got this exponential growth. Exponential growth, population's growing, and then all of a sudden you have fire. is fire a density dependent or density independent effect? Density independent effect. What was the effect of fire? Devastated the food supply. So in this case, we have food supply basically regulating our population. Population was growing up. Fire basically destroyed all of the food, basically the food that the moose are eating. You know, they're going to be grazing out there. Population size crashed. And then population was going to start to increase. And then we had another harsh winter. Another ice bridge formed, and wolves then colonized this island. All right? Wolves colonized, and now at a time, our population should start to go back to this increase, and it didn't. It started to increase, and then it was depressed and actually stayed low. Here's a case of top-down regulation. Predation now is regulating our population. All right? And you have basic relative stability between our two populations, and then you have heavy snow in the, around the 1970s, late 60s, early 70s, winters of heavy snow. That had an effect on our populations by giving our moose a reprieve, so it's harder for the wolves. Wolves' populations declined. That allowed our moose populations to increase. All right? And then, once the snow went away, wolf population, with a better food source for them, more food source, wolf populations took off. You see our top-down control again until canine parvovirus hit. Canine parvovirus, density dependent or density independent effect? What do you say? What's that? Dependent. We have a vote for density dependent. You agree? Yeah. All right. If I asked, is COVID-19 density dependent or density independent, what would you say? Same thing? Density dependent. Yeah, so diseases, especially infectious diseases, they operate in a density dependent effect. As you increase population size, increases density, makes it more likely to transmit the virus, and if the virus causes death, you get population control. So yeah, it's canine parvovirus. When it came in, could have been just a random chance of it getting there, but once it was there, it's operating in a density dependent effect. That's definitely going to cause a decrease in our wolf populations. Decrease in wolf populations allowed our moose to increase, and then you have winter ticks. That had an effect, introduced some disease, and deep snow. Deep snow blocked the food source over the winter of our moose, causing a decrease, and so forth. So what we're showing here is that you have many different factors that are regulating these populations. But there's really only one dominant factor that was operating at any one time. You had food supply operating. You have predators operating. All right? You had your random density independent factor with the fire regulating there. All right? You have all these different factors that are at work. In some cases, the factor's working on another species that it's interacting with our species of interest. So if we were interested in only the moose populations, we have to recognize that the predator's having an effect, and anything that affects our predator populations will also affect our moose populations. How do we figure this out? We really can't. That's part of the contingency in ecology. We don't know what's going to happen. We don't know what our starting conditions are like. We don't know how randomness and uncertainty is going to affect our outcomes in the future. So what happens here at this Isle Royale in Lake Superior may not apply to another island in another Great Lake. It could be completely different. All right? Questions? Nope. All right, we're going to stop here. Yep, Kyle, density dependence need more numbers. So yeah, with our viruses, bacterial infections, more individuals that are there, the more likely the virus, bacteria spreads. They operate in density dependent fashion. All right. We'll end here. Lab today, don't forget. We're going to do some calculations. So bring calculator, bring your computer. You can bring your computers, tablets. I'll show my class how to use Excel with these problems. And if you have questions, don't forget the quiz and the practice problems. If you have questions, please email me.